Okay, so this video is going to discuss Chapter 16, Section 5 on so-called relative motion analysis. Okay, so the goals today will be that you will be able to describe the motion of a rigid object in terms of a combination of translation and rotational pieces, and you will be able to perform the so-called relative motion velocity analysis of a point on the body. All right, so usual thing, outline's pretty much a standard one. All right, so the reading quiz. So hopefully you've read section 16.5. So question 1, when a relative motion analysis involving two sets of coordinate axes is used, the x prime, y prime coordinate system will be, will A, be attached to the selected points for the analysis, or selected point for the analysis. B, rotate with the body. C, not be allowed to translate with respect to the fixed frame. Or D, none of the above. All right. And question 2. In the relative velocity equation, V, B slash A, that is A, the relative velocity of B with respect to A, option B, due to the rotational motion, C, omega cross R B slash A, or D, all of the above. So take a second, think about those. Okay, so if you've done the reading, you'll know the main point of doing in the relative motion analysis for velocities is to kind of separate translational and rotational motion. And the x prime, y prime coordinate system is the coordinate system which follows a fixed so-called basis point as it translates, and then relative to that, other points in the body are rotating. So anyway, so for question 1, the correct answer is A. And for question 2, they're all correct, because in the relative motion analysis, the relative velocity of B relative to A is the part of the velocity of B which is not just a simple translation. It is only the rotational portion. So option A is just the definition of V, B slash A, and B and C are really the same thing, one in words and one in equation. So the correct answer is D, all of the above. Okay, so here's a situation that's kind of a scenario that's given. You have a slider block A, and it moves horizontally to the left with some velocity, and it causes the link CB to rotate counterclockwise. So there's some sort of, okay, so their VB is going to be only allowed to move tangent to the circular path traced out by kind of the cam right there at kind of centered at C. So you can think about which link is going to undergo general plane motion, link AB or link BC? Well, pretty clearly, link BC is rotating, so that's just rotational. So AB must be undergoing general motion, and so that means that the link AB must be moving with some combination of translation and rotation. So how could you figure out the angular velocity, the rotational part associated with link AB? That's the kind of question we want to ask. Other types of problems are when you have planetary gear systems, so you have nested gears. How can you relate the angular velocities for different pieces of this, or different components of the system? All right, so relative motion analysis. The basic idea is encapsulated in the top figure. So if we follow the cursor here, we imagine there's a rod, AB, and it moves in time from left to right. So you can tell kind of the relative positions of A and B are changing in time. The main idea of a relative motion analysis is to pick a point that you usually already know its motion. Maybe you already know its velocity, for example. So maybe we already know about point A and how it moves. Okay, so you can see the point A moves from a position here over to a position, here with so it moves from here to here. And let's imagine that we know that motion. Then, so what you could imagine is that if you already know the motion of point A right here, then you could imagine hypothetically what a translation alone would do to point B. A translation alone would simply move point B up to somewhere right around here. And you can see over here on the right, that's what they've got. This B prime point that they've indicated represents the hypothetical location of B if it only underwent translation. Okay, so that means that's what you would get if A and B kind of moved together under a translation. All right. But that's not what B does. B moves more than just that, and B actually goes all the way over to here. So B follows not just a translational path, but it also undergoes a rotation as it moves. Okay. All right. So get rid of that. Okay. So B not only translates, it also rotates. So the idea of a relative motion analysis is to kind of decompose the motion of B into a piece which translates along with the basis point, which we're calling A, and then a component which is due only to a rotation. Now, when you have a translation, everything moves together, so the relative displacement is zero. So the relative displacement is the part of B's path which is not a translation. Therefore, the relative motion part, the relative differential, is the part which is due to a rotation. So it's going to look just like a pure rotation did when we had a fixed axis last time. Namely, it's going to be related to omega cross r. Okay. Sorry. Okay, so just kind of carrying through. Here's another, well, this is just basically just dividing everything, all the differentials by time, and using the fact that for a rotational motion, you can write dr dt as omega cross r, as we found last time with the fixed axis rotations. So here's an example where they've got an object, and what happens is actually the top point moves forward and the bottom point actually moves backwards. So what they've done is they've kind of decomposed that motion, the forward on the top and the backward motion at the bottom, as well. First they imagined that both the top and bottom hypothetically both move together equally. That would be a translation. And then what you have to do is, since the bottom point actually moved backwards, then the rotation would, well, first of all, the rotation vector doesn't do anything to the basis point because it's the fixed point of the rotation. And then the rotation component then acting on at B actually gives a long kind of backwards vector, right? So what they have here is that this vector plus this large backward vector equals the kind of relatively small backwards vector. That's kind of pictorially what's happening. Okay, so this is just a useful way to analyze problems if you know what one position on the rigid object is doing, and it allows you to kind of track other rotations about that fixed point. All right, so for example, we know things about, the system. So take a second, think about what you know about motions here. Okay, so for example, let's imagine we're thinking about link BC. We know that point C has 0 translational motion, which means the only motion, so there's no translational velocity associated with C, which means that you're only going to get rotational motion for point B. And it's got, and that means point B has to follow an arc of an appropriate radius. So that's one thing. So that's one way, because we know something about point C, that gives us a simplification for what can happen for point B. Similarly, we know that point A can only move horizontally. Okay, so that means, well, so what you could do is, because we know point C is fixed, therefore point B only moves along an arc, that would allow us to figure out the velocity at point B. And then for the link AB, you could use point B as the basis point to figure out the motion of A relative to it. Another really common use for this is when you have an object that rolls without slipping, you know that relative to the ground or the surface of contact, the contact point has 0 velocity. So it's oftentimes very convenient to think of the velocity of the center of a wheel or an object that spins or that rolls without slipping as the velocity of the contact point, namely 0, plus a rotation about it. So that just simplifies the analysis. Okay, so the basic procedure is going to be to first fix an absolute frame, and then you're going to want to draw a kinematic diagram and establish a magnitude and direction for the relative velocity vector, and then write out the key addition of velocities formula, and then break it into components and then solve for any unknowns. But this is the main equation. Okay, the main equation looks like this. Or in terms of vector analysis, you're going to identify various vectors and then write it out in components. Basically just work out the cross product and write it out in components, and that's going to give you two equations and two unknowns. You can use that to solve for any unknown that you might have. All right. So next up, we have a couple examples that I want to work through, and I wasn't very happy with the way the last couple of videos went, so I'm going to work this out on the whiteboard. That seems to be a little easier for me. Okay. Okay, so I'm going to switch over to the whiteboard now. Okay, so hopefully this isn't too bad. That looks awfully, I hope there's not too much glare. We'll give it a go. Okay, so for this problem, I should have held that up a little longer. So I tell you what, I'm going to quickly go back, and you can, well, you guys can pause it. You don't have to do that. So in this problem, what we have is so this would be 16.5 example 1. So in this problem, we have a wall and a ground, and we have a rod which is connected to two rollers. So what's going to happen is this object is going to roll, this side is going to roll down, and simultaneously this end is going to roll to the right. So the overall, it's going to kind of fall, and so it's going to move over and rotate. So it's going to fall down. So it's a combination of translation and rotation. We are told that, so we're going to mark these points. We'll call this B, and we'll call this A. And we're told that initially the velocity of A is to the right, and it equals 3 meters per second. And we also know just from the diagram that the velocity of B is down, right? Because if A is moving to the right, it's going to cause the rod to rotate down. Right. Furthermore, the problem also tells us that initially this angle is 30 degrees. All right. Okay. So let's think about this here. The the point that we know lots about is A. We know it travels along the ground at a constant velocity. So we should make that our basis point. And then if that is our basis point, so basis point is going to be A, then what we need to do is work out, well, first we want to write out R of B relative to A. Okay, so relative to A, how's that going to go? Well, and I'm just going to call this angle theta more generally. Okay. All right, well, I see that R of B relative to A is, let's see, it's simply going to be negative, oh, I should have also said this. The length of this is 1.5 meters. Okay. So that tells me that the position of B relative to A is going to be negative 1.5 cosine of theta in the x direction and plus 1.5 sine theta in the y direction. Now, question about minus signs. And I believe the way they defined it, I'm trying to look here. No, they didn't actually give you a definition of that. So what we're going to have, so we know what's going to happen. This thing is going to swing down, and it's going to, so if I'm measuring theta in a, let's see, if I measure theta in the positive direction, so if I say down is a positive rotation, then I have to be a little careful here. Let me think about this for 1 second. Yeah, that's okay, like that. All right. I'm a little worried about minus signs here. Excuse me. All right, well, I'll just follow my notes. Seem to match their answers. Okay, so now if I have that, I can immediately write down, well, so if you think about it then, we can then say that the velocity of B relative to A, or sorry, can be written in terms of the velocity at A plus omega cross the velocity, the position vector R B relative to A. Okay. Now, I know that omega must point in the z direction. So omega vector must be proportional to z hat. In which case, I can write this out as VA, well, that was nothing other than 3 meters per second x hat plus omega. Well, omega has some magnitude, which I don't know, and I'm going to get z hat cross R BA. this quantity that I just wrote down. And you have to think about z hat cross x hat, that's going to be a positive y hat, and z hat cross y hat, that's going to be a z hat cross y hat is going to be a negative x hat. So this comes out to be x hat times 3, and then I get plus omega, so I get z hat cross y hat is minus x hat, so that's going to be minus 1.5 sine theta times omega plus y hat, and that comes from the cross product alone. That's going to be, so I'm going to have an omega coming from here, and I have z hat cross x hat. That gives me y hat, but there's a minus sign out front. So I end up with a minus that times 1.5 cosine of theta. Okay. Whew. So that's what I have. And very good. Now, that's okay. So this is where I am. And then I'm describing the velocity of B. So let's restep, go through the steps. I kind of write down the things I know, and then I write a general formula for the relative vector. Then I plug it into my relative velocity formula, namely the velocity of the point I want equals the velocity of the basis point plus the rotational term. I just plug everything in, take the cross product, and then I get an equation in terms of, different basis vectors. That needs to be equal to the velocity in the B direction. Well, I know that the velocity for B, points straight down. It's in the negative y direction. So what that means is that the left-hand side should be 0 in the x direction and plus something in the y direction. All that's telling me is that I can set this coefficient of x hat to 0 and only the y component survives. I'm just going to make some room here. So what I get is that the 0, because B is only moving in the y direction, it's not moving in the x direction. So this x component of velocity better be 0. Right? And furthermore, it lets me say then that the velocity of B in the y direction, which is the only way it's moving, equals minus 1.5 times omega times cosine of theta. Now, in the problem, they told me that theta was 30 degrees. All right, well, so now I can take this, plug it into the top equation. So sine of 30 degrees is a half. So this tells me that 3 minus 1.5 times a half equals omega. So that means that omega must equal 3 divided by 1.5 divided by a half, which equals 2, and it'll come out as radians per second if you're careful with the units. Okay? Oh, I fouled it up. What did I do wrong? Oh dear. 3 divided by 1.5 was a 2, and then I have another half. So this is 2 times 2, it's a 4. Sorry, doing too much in my head. All right. Now, if that's omega, then you can plug that into here. And since we know the angle is 30 degrees, you get 1.5 times 4 times cosine of theta. And we get that the velocity for B, which is only in the y direction, is minus, from here, and I get 5.2 when I multiply it out, meters per second, y hat. Now, an observation here. Notice, I found a positive angular velocity, and that makes sense because I chose an angle that was defined to be counterclockwise, and the rod fell in the direction of my of kind of increasing angle from the way I defined increasing angle, matching the mathematics or the math class definition. If you had chosen the angle to be reversed, that would have been okay, but you would have had to flip the minus sign because you would be reversing the definition of theta, which causes all of the sine functions to pick up a minus sign. And so you have to compensate by tweaking the formula for the relative vector by hand. So you have to be careful. You have to pick a coordinate system, and once you make your choice, you have to live with it. Okay. Let's do another problem. We'll go back and you can see the PowerPoint slide. Okay, so, just to see that we were right, it matches. Omega is 4, and the velocity was negative 5.2 meters per second. So that came out the way we wanted. Okay, here's another problem. So we have a crank which rotates, and it's going to rotate rod OA with an angular velocity that's given, and we take it to be a constant, as 12 radians per second. And it's going, if you look at the diagram, you can see it's rotating counterclockwise, so that'll be a positive angular velocity for rod OA. So as that happens, that's going to cause the slider to move. The piston's going to go to move. So what we want to do is to find the piston's velocity, and then let's find the angular velocity of rod AB. Okay, so this is a little bit more complicated than the last analysis. So when you see something like this, the first thing you should be thinking is, are there points that I know lots about? So obviously, you know that point O is fixed, which means about point O, point A only rotates. It's only allowed to move tangent to the circle defined by, with radius by the line segment, by the rod OA. So point A follows on a circular arc because the rod is rigid. Okay, so that means we know a lot about point A. As far as point B is concerned, the only thing we know is that the x component of its velocity is 0. That's the only thing we know about it. So take a second there, take note of the numbers for the various relative sizes of things. And then we're going to use those facts to solve for the velocity of the piston and the angular velocity of rod AB. This is very much the actual method, though, is going to be very similar. Okay, so we're going to write down all the things we know. We're going to try to write down a formula for the relative vector, RBA, and then we're going to just kind of write out the arbitrary cross product and get our result. Okay, so if you hopefully you have that transcribed, and now I'll switch over to the whiteboard. Okay, so hold on, make sure I have my video working. Okay, good. So now we're going to do, so this is going to be 16.5 example 2. So the diagram that I have here is I have point O, I have point A, which is straight above it, and then I have, or here, I have point B. B is only allowed to move vertically up and down. A follows an arc. Maybe label that. So B is constrained to only move vertically up and down. A has to follow an arc like that. So A has to follow an arc, and B can only move vertically. The problem tells me the following dimensions. I know that this is 0.3 meters, and I know that this is 0.6 meters. And the problem also tells me the initial angle. So maybe I should make that a little smaller. Okay, so this is, here, I'll put it over here. I know that the length OA is 0.3 meters. I know the length from AB is 0.6 meters. The problem also tells me that this angle right here is 30 degrees. Right? As is usual, I kind of prefer to leave things as with an arbitrary angle and then substitute in at the end. That's helpful sometimes if you want to take extra derivatives to figure out accelerations and things. Okay, now we're actually going to do this kind of a little longer than what I think the book recommends. We're going to do a relative motion analysis on OA, or rod OA, to find the velocity of A. And then once we know the velocity of A, we'll do a relative motion analysis on rod AB to find the velocity of B. Mostly just to practice. All right. The problem tells me that omega for OA is 12 radians per second. So this rod rotates with an angular velocity, a scalar angular quantity of 12 radians per second. Which means that if I want to turn that into a vector, I'm going to have that omega OA vector is 12 radians per second z hat, because it's rotating counterclockwise. Furthermore, if I want to use a relative velocity analysis, then I need to write down R A O. Well, that's nothing other than 0.3 meters times y hat, because the relative vector from O to A points vertically straight up. Okay, so then my relative velocity analysis would say that the velocity at A equals the velocity at O plus the relative velocity of A relative to O. Now this is particularly simple because point O has no velocity. It's stationary. So this is all I get. And I see that the velocity of A is, in fact, just omega OA cross R AO. And we just wrote those vectors out. That's 12 radians per second, z hat cross 0.3 meters y hat, okay? And z hat cross y hat is a negative x hat, so we find that this velocity vector is, typing in the numbers, you're going to get negative 3.6 meters per second x hat, which kind of makes sense because if it's rotating clockwise, then when point A is here at the top, the velocity it should be in the negative x direction. And I get negative 3.6 meters per second x hat. Okay, so that's a useful thing to know. All right, I'm going to erase that to make room, but we will need that number. Okay, so we have found the velocity. We now know that the velocity of point A is negative 3.6 meters per second x hat. So we know the velocity of A. The problem asks us to find the velocity of B and also the angular velocity of the rod as it rotates. So to do that, I'm going to say that the velocity of B equals the velocity of A, which we now know to be this, plus omega AB, the angular velocity of the rod AB, cross the relative vector from A to B. All right, so to apply this formula, I need to come up with an expression for this one, R B slash A. So that's a vector which points from A to B. So it's going to be a vector from A to B. And I know that in the problem they tell me that the angle is 30 degrees, but I'm actually going to just call it theta. And I'm going to say that we start at the x-axis and we go down. It's actually going to be theta, and theta is actually going to be negative 30 degrees. For really being careful, trying to be careful with my coordinate system, I'm measuring theta from the x-axis, so I actually have to go down 30 degrees. So I'm using, the magnitude has to be 30 because of opposite interior angles. And if I'm being careful with minus signs, that's what I get. Okay, so then that lets me say that R BA equals, well, it's going to be cosine of theta times, and the length of this thing was 0.6 meters. So that's going to be 0.6 meters times cosine of theta x hat plus 0.6 meters sine of theta y hat. And you might be saying, why do I have a plus sign? Because it's clearly going down. Well, the minus sign is taken care of because I have a negative angle. So if I use a negative angle, then I get a plus sign. If I'd reversed the angle and said that the angle was positive, then I'd have to put an explicit minus sign in by hand. And then the problem I would have, well, not problem, but then what would happen is I'm actually measuring the angles, I'm kind of all my angles are backwards, and I'm actually going to get a reverse of my angular velocity will come out with the wrong sign. Well, it would be the right sign, but with an unusual coordinate system. So if I'm using the standard math definitions, then I should choose this to be a negative 30 down, and then I will, everything else will come out correct. Okay, so now the velocity of B can only be in the y direction. That means when I work out the x component, it'll have to be 0. I already know the velocity of A, found that, and I just deduced the form of the relative vector. So I can use this vector equation to solve for the angular velocity and then solve for the actual velocity of point B. Okay, so we're going to need to write this down. So I'm going to need to make room to do this. But remember, the angle, when I actually substitute in, will be a negative 30. I'm going to write that up here. Theta equals minus 30 degrees. Okay, so plugging in everything I have, I know that this vector can only be in the y direction. It has to equal, so I'm going to get negative 3.6 x hat coming from VA plus omega AV, which is in the z direction, cross the vector I just had, which was a 0.6 0.6 cosine theta x hat plus 0.6 sine theta y hat. So when I work this out, I just keep coming back to the same point. Z hat cross x hat is positive y hat, and z hat cross y hat is negative x hat. So this says that I get x hat times negative 3.6 coming from the first term, and from over here I get minus omega AB times 0.6 times sine, and I'll go ahead and plug in here, negative 30. And so that's here, I get z hat cross y hat, that's negative x hat. So that's this minus sign. And then the angle is negative, and I have 0.6, yeah, okay, I've got it all taken care of. And then I have plus y hat times omega AV times 0.6 times cosine of negative 30. Whew. Okay, sine of a negative angle is negative, so that's the same as working with plus sine and plus angle, and I get that omega AV equals 3.6 divided by 0.6 divided by sine of 30, which is a half, and typing them all in, I get 12 radians per second. Positive. Does that make sense? Well, I measured my angle. I said that going down was a negative angle. So as this thing rotates, what I'm expecting then, in fact, if you think about it, if this rod rotates clockwise, that's going to make this rod up on top swing up. So that's going to, in fact, be a positive change in angle per unit time. So that makes sense visually. Okay, so, and then after we find that number, we have to substitute that into here, and we can work out the velocity. It'll be positive because cosine of negative 30 is the same as cosine of 30. and when I multiply it all out, so all I'm doing is substituting in and multiplying this term, I get that the velocity for B equals positive 6.24 meters per second. And it's only in the y direction. So that's a second example, how to do this. So in both the last two examples, the process was basically the same. You kind of write down the stuff that's given. You identify points where you know a lot about the motion, namely, is something a fixed point? Or is something moving on a circular path? Or is something moving only in a linear path where you can set one of the velocity components to 0? And then you're going to use the relative velocity formula, and you start writing out, using your coordinates, writing out formulas for the relative vectors given, of 1 point relative to a basis vector or basis point. And then you plug it into your relative velocity formula and you just solve for the unknowns. It's just algebra from there. There's no real mystery to it. So in the first problem, we just had to do it once. In this problem, we didn't have to do it the way it's kind of overkill, but I did it twice. And that can happen, right? You just sort of, if you have a complicated chain of things, you might have to just sort of go use the relative velocity vector to get from one point to another, to another, to another, and just kind of zigzag your way through the system. Okay, so hopefully that was a useful example. We can just check. I think this matches what they had, but let's just check. And the way I did it might be a little different, but the underlying strategy is going to be the same. No, it's pretty much the same. They just jumped immediately to saying that they knew the velocity at A, and you could have done that. That's basically physics 1 technology there. But having done that, they wrote out the relative vector. They wrote it all out with just an unknown angular velocity, and then they kind of came up with a coordinatized version of the relative vector. Notice they kept theta positive, but then they put an extra minus sign in by hand. So it's okay. You just have to kind of know what you're doing. Basically, pick a coordinate system, live with your choice, and then the numbers worked out the same. So good, math works. All right. Okay, so here's your concept quiz. We're going to start class with this, so take a second, read it, and I will ask you to answer these questions when we start. So in face-to-face, what we will do is go through this and then also go through the group problem together. Okay? See you guys.